In April 2025, a team of astronomers published a paper. It was peer-reviewed, it was careful, it was written by some of the most respected astrophysicists on the planet, and buried inside it was a sentence that, if true, changes everything. James Webb had detected a chemical in the atmosphere of a distant planet, a chemical that, on Earth, is produced by exactly one thing: life. The planet is 120 light-years away. It orbits a star that science has long considered hostile to living things. And the chemical was there, floating in its sky, measurable, real. Nobody has announced a discovery. Nobody is claiming proof. But the signal exists, and no one can explain where it came from. The telescope that found it is the most powerful astronomical instrument ever built. The James Webb Space Telescope launched on Christmas Day 2021 and spent the next 18 months positioning itself 1 million miles from Earth, unfolding a golden mirror the size of a tennis court. It was designed to see things no human had ever seen before, to peer into the atmospheres of distant worlds and read what was inside them. Light from a star filtered through a planet's atmosphere, as the planet crosses in front of it, carries a fingerprint. Every molecule absorbs light at a specific wavelength. Webb reads those wavelengths. It reads the chemistry of worlds it cannot visit. And in 2023, it turned that mirror toward a planet called K218b. K218b was discovered in 2015 by the Kepler Space Telescope. It sits in the constellation Leo, 120 light-years away. It is 8.6 times the mass of Earth, which puts it in a category called a sub-Neptune. It orbits within the habitable zone of its star, the band of distance where liquid water can theoretically exist on a surface. For a long time, it was considered a curiosity, a planet in the right place around the wrong kind of star. K218 is a red dwarf, a class of star that makes up roughly 75% of all stars in the Milky Way. Red dwarfs burn cooler and dimmer than our sun. They live for hundreds of billions of years, and they are extraordinarily violent. Red dwarfs blast their nearby planets with ultraviolet radiation and X-ray flares at intensities that would strip away atmospheres and sterilize surfaces. For decades, the scientific consensus has been that red dwarf planets are poor candidates for life. Too much radiation, too unstable, the wrong kind of star. That consensus is now uncomfortable. The Cambridge team studying K218b, led by astrophysicist Niku Madhusudan, had been developing a new framework for thinking about planets like this one. He called them Hycean worlds. Hydrogen-rich atmosphere, a vast liquid water ocean beneath it. The hydrogen layer, thick and dense, might act as a shield. Life in the ocean below, insulated from the radiation above, protected by miles of ocean above it, and atmosphere above that. It was a hypothesis, an interesting idea, a reason to look more carefully. So they looked. Webb observed K218b using transmission spectroscopy. As the planet crossed in front of its star, the telescope captured the light that passed through the planet's atmosphere. It found carbon dioxide, it found methane, both expected, both consistent with a Hycean world. And then it found something else, a signal in the data that the team initially treated with caution, a signal they checked again and again and again, a signal that, by April 2025, had been confirmed across multiple independent observations. The signal was dimethyl sulfide. The chemical formula is simple: 2 carbon groups, 1 sulfur atom, a handful of hydrogens. Dimethyl sulfide. Scientists abbreviate it DMS. On Earth, it has a distinctive smell, the slightly sulfurous scent of the ocean on a hot summer day, the smell of the tide coming in. If you have ever stood near the sea and caught that particular salt and something else note in the air, you were smelling dimethyl sulfide. And dimethyl sulfide on Earth comes from one source: marine phytoplankton, microscopic organisms that live in the surface layers of the ocean, converting sunlight and nutrients into energy, releasing DMs as a byproduct of their metabolism. It drifts into the atmosphere in enormous quantities. On Earth, it accounts for more than 90% of the sulfur that enters the atmosphere from natural biological sources. It is, in the most direct sense of the word, a signature of life. Here is what matters. Scientists have searched extensively for ways that DMs could form without biological help. Abiotic pathways, chemical reactions driven by radiation, heat, or geological processes that could produce detectable concentrations of dimethyl sulfide without any living organism involved. They have not found one. On Earth, in laboratory conditions, the chemistry doesn't cooperate. DMs in planetary scale concentrations requires organisms. It requires biology. It requires something alive, processing energy, and exhaling a byproduct into the sky. In the sky of K218b, 120 light-years away, orbiting a star that was supposed to be incompatible with life, has it. The team is careful. Niku Madhusudan and his colleagues have not claimed discovery. They are scientists. They know what a claim of extraterrestrial life requires. They know the history of premature announcements. In 2020, the same team of researchers announced a possible detection of phosphine in the atmosphere of Venus, another chemical associated with biological processes. It sparked global headlines. Then other teams re-examined the data and found the signal was likely instrumental noise. The field became cautious. Burnt once. The K218b DM signal is something different. It has been replicated. It has held across independent analysis. The confidence level is significant, not yet at the 5 sigma threshold that physics demands before calling something a discovery, but well above noise. Solid enough that the paper was peer-reviewed and published. Solid enough that the scientific community is taking it seriously rather than quietly dismissing it. What this means depends on which question you are asking. If the question is whether life exists elsewhere in the universe, the answer from K218b is not yet. Not confirmed, not proven, but possibly. And possibly in this context means something it has never meant before. Every previous candidate for extraterrestrial life, every Mars rock, every phosphine signal, every extremophile analogy has been circumstantial at best. The K218b signal is direct. A specific molecule, known on Earth to require biology, detected in the atmosphere of another world. That's a different category of evidence. It is not proof, but it is the closest we have ever gotten, by a significant margin. If the question is what it tells us about the universe, the answer is stranger still. 75% of all stars are red dwarfs. For decades, we have been effectively writing off 75% of all planetary systems as places where life could not take hold. If a Hycean world around a red dwarf can harbor life, that calculation reverses. The number of potentially inhabited worlds in the Milky Way alone jumps by an order of magnitude. The universe that seemed empty starts to seem crowded. The silence that puzzled us starts to seem like it requires explanation. Webb will observe K218b again. More data is coming. The signal will either strengthen or weaken under scrutiny. If it strengthens, if the DMs holds at higher and higher confidence levels across more and more observations, there will come a moment when scientists have to say the words they have never said. If it weakens, if a new instrument finds the signal was atmospheric noise or an artifact of the telescope's own chemistry, the question goes back to open. Either answer will be important. But right now, tonight, the data is what it is. A chemical that life makes, detected in a sky we cannot reach. A signal hanging in the atmosphere of an ocean world, orbiting a violent red star, 120 light-years from everything we have ever known. We do not know what made it. We do not know if something is out there, doing what living things do, completely unaware that we are watching. We just know it is there. And that is the most extraordinary sentence in the history of science.